Okay, we should start. So, switch that. Keep fogging up. All right. Okay, so we had the lab, so I don't think we need a huge intro in this, but what we're going to be doing next, for the next 2 weeks, is go over covalent bonds. 222 will cover ionic bonds and metallic bonds, which nobody really thinks about sometimes, but we're going to focus on covalent bonds. We're going to start off, of course, with Lewis structures. And you saw in the lab we did the shape. We're going to take that shape and understand what it does for us. So we're going to talk about polarity. We're going to get into how those shapes are made using the concepts we've already learned. So we've learned about s orbitals and p orbitals. And I mentioned that when bonds form, the orbitals have to overlap. So how do you go from p orbitals? So if I have an atom that has these p orbitals, one's going that way, another's going that way, and then the third one's going in and on the board, all 90 degrees from each other. And of course there's the s orbital spherical. How do you go from that to tetrahedral, where everything is 109.5 degrees? So we're going to talk eventually about what it takes to go from this kind of orbital to this kind of bonding model. Like, where's the disconnect? We haven't kind of figured that out yet. Then we'll get into molecular orbital theory, which is a different way to think about bonding. It's less visual like this is, like Lewis structures are. But it'll be a nice intro to if you take 222. So we're going to try to get all of that done in the next 4 lectures. We'll probably finish in plenty of time. We'll have some time in the 4th lecture to kind of review a little bit. But that's what we're going to do. So let's start off with something we've already looked at, covalent bonds and Lewis structures. We might go through this a little bit quickly. But, I forgot my clickers. So, the covalent bond is essentially 2 nonmetals creating a bond between each other. That bond is something that is that connects them. And so we're going to use a simple model. We're going to use our, let me start this before we forget. Almost there. Got bogged down by emails before this, sorry. All the people taking spring term, they were like, can we do this remotely? I'm like, nope. All in person.
Wait, I think there's a few classes that are not in person.
There are a few remote lectures, but the labs are pretty much all in person. They've decided that, yeah, it's too important. Mm-hmm. If we kept doing remote labs, like 2 years ago, for the past 2 years, it's been an emergency situation. Everybody's done it that way. But now that every college is doing pretty much in person, if you continue to do remote labs, you could risk losing accreditation. That's the idea that if you take a chem class here, another university won't count it, because it's not a fully fleshed out chem class with labs and stuff.
Okay.
So it's better this way for you guys too, even though it's theoretically riskier. So going back to this, here's our core charge model. So we're boiling down the core charge model to simple Lewis structures. So you notice that it's the same thing, the idea there's 7 valence electrons, 7 valence electrons. We're just kind of ignoring the core charge part. We're just going to put the name of the atom. And that's basically what a Lewis structure is. The Lewis structures we were drawing in lab today, I mean, the big part of it is we're showing where all of the valence electrons are. That's why we counted total valence electrons. That's why we made sure that we tracked them all every single electron was accounted for in our picture. There we go. There's some Lewis structures. This is easy. I think we're going to skip some of this. So yeah, I don't want to go through that. This is kind of too easy here. So how do those covalent bonds form? Like what are they doing when they form this covalent bond? Well, what you're seeing here are two spherical atoms. We're not really looking at anything specific, but if you remember, hydrogen has the 1s orbital, so you can almost think of this as the 1s orbital of the hydrogen where the electron's located. Well, those orbitals, they overlap a little bit, like the boundaries of the atom, right? How is an atom defined? Like where is the end of an atom? Well, it's like somewhere where the electron kind of stops finding the electron. So here we're showing that these atoms are overlapping slightly where their electrons are, but they don't get too close. So let me pull this up. Actually, this doesn't work. Let me find real quick. Actually, maybe it does work. Let's try that. No, it doesn't. Okay.
A covalent bond consists of a pair of electrons shared by a pair of nuclei. Let's use this graph. A covalent bond consists of a pair of electrons shared by a pair of nuclei. Let's use this graph of potential energy versus the distance between the nuclei to see the change in energy as the distance decreases. We'll pay most attention to the bond in H2 and then look at Cl2 and larger halogens, defining two key bond parameters along the way. When the H atoms are far away from each other, we designate the energy as 0. As they move closer together, they attract each other more and more, and the energy decreases to a minimum. At this point, a stable hydrogen molecule has formed. If the nuclei come any closer, the energy increases rapidly as nuclear and electron repulsions take over. Now let's zoom in closer to see the overlapping atoms in more detail. When the atoms are far apart, they do not feel each other. But as they come closer, the nucleus of one atom attracts the electron cloud of the other, and the attraction draws the atoms still closer. Note the increasing electron density between them. Soon, the electron clouds interpenetrate. Attractions dominate, but repulsions between nuclei and between electrons become stronger. At the point of lowest energy, attractions just balance repulsions, and the two H atoms exist as an H2 molecule. The covalent bond is the mutual attraction between the nuclei and the electron pair. If the nuclei were to move closer, repulsions would outweigh attractions. The increase in potential energy would destabilize the system and the atoms would move apart again. In reality, the molecule vibrates, the atoms moving slightly farther and closer at the point of minimum energy. The bond length is the average distance. For H2, it is 74 picometers. The bond energy, the difference between the minimum energy and the starting point, is the energy needed to break a mole of H2 molecules into separate H atoms. For H2, it is 432 kilojoules. Now let's...
So really quickly, they showed you that that vibration, which is the atoms are actually not staying still, or they're vibrating, they're moving closer and further, like on a spring. And that's true. And I don't want to complicate things, but I'm going to. But don't worry about it for the exam or anything like that. Remember that we're still living in the quantum world, or at least the atoms are. And so this concept of vibration, and you can see how it goes back and forth. It's a nice, simple idea to think about, but remember, atoms live in the quantum world. The energy of vibration is quantized too. So it's not any point. It's not like they can exist anywhere here. They exist here, here, in specific energies, vibrational energies too. So I just wanted to point that out because quantum stuff is nightmarish and crazy complicated and weird. So even though it's nice to think, oh, it's like a spring, yeah, it's a simple model, but it doesn't really act like that. It's more weird than that. So let's continue to think of the simple model, but I just wanted to make sure that in the back of your mind you're like, oh, it's actually weirder than that in real life.
Let's compare H2 with Cl2 and other halogen molecules. The much larger chlorine atoms reach the energy minimum and form a Cl2 molecule at a greater internuclear distance. Because the Cl nuclei are farther apart, it takes less energy to separate the atoms, thus a greater bond length and a smaller bond energy. Moving down group 7A, bromine is larger still, so we would expect an even greater bond length and smaller bond energy. And iodine, the largest of these halogens, continues the trend to longer, weaker bonds. Stepping back, we see that in each case, mutual attractions draw the atoms together and they form a covalent bond of specific length and energy.
Anyway, we're going to summarize that real quick. So, that's just the generic picture you saw before in the video. This is distance between two atoms. They're really far apart. The energy is practically zero. There's no attraction, no repulsion. And as they get closer together, they start feeling each other. There's an attraction. And the attraction is between the nuclei of one atom and the electrons of the other atom, and vice versa. That's the major driving force towards them coming together like this. And down here, this distance here, this is the best possible position to have the maximum attraction, based on Coulomb's law, but also balancing out the repulsions, because the nuclei of one atom and the nuclei of the other atom, they're both positive, they repel. And the electrons of one atom and the electrons of the other atom, in this case one electron for hydrogen, repel as well. So there's this competing repulsion and attraction, and that is the point where you have this perfect balance. So that defines how long that bond's going to be, what distance those two atoms are going to have from each other. This is exactly the same thing. And so from these kind of charts, you can get a bond length and the bond energy. So what is this bond energy? This tells us, we can read backwards and we can say, well, if I put in positive 432 kilojoules of energy, I'll bring it back to zero, which means I'm breaking the bond. If I have H2 and I add 432 kilojoules of energy, I will break the bond. Okay? This is just like ionization. We're bringing it back to zero. Okay. So yeah, there we go. It's a sum. It's basically the covalent bond is just a balance of all of these attractions and repulsions. All right, so we'll start with the first clunker question. If I state this, two hydrogen atoms come together to make hydrogen, and this energy, what would you say it's an exothermic process or an endothermic process? So these are probably new words, maybe. Exothermic means you release energy. Endothermic means it requires energy. How would you think about that? So making that bond, what does it do? Get it straight in your head. Another 6. Okay. We're getting smaller and smaller over time. Okay, so I expected it. It's a little bit confusing. So the answer here is it's A. It's an exothermic process. So one way you can think about it is going back to this chart. When I make this bond, now the molecule's energy is lower than it was before. So how did it get lower energy? There has to be a conservation of energy. If the overall molecule's energy is lower than what it was, it needs to get rid of that extra energy that it used to have. And so it's releasing energy to make the bond. When you make this bond, it releases energy to the surroundings. Okay? So making bonds is definitely an exothermic process. All right, that's kind of what this equation is saying here. We're putting two hydrogens together to make H2, and there will be some leftover energy that comes out of this. So that energy used to be part of the hydrogen atoms alone, but when the hydrogen atoms make hydrogen in the molecule, that energy is released to the surroundings, to somewhere. Okay. And you'll do energy stuff a lot more in 222. Okay, this is good. So we're going to come to the. I mean, some of this will be easy, I think, but we're gonna look at the table in Chem Activity 13. We're going to answer some questions 2 through 10 on page 226. Just kind of make sense of what these numbers do for us, and when we see these numbers and how they relate to the kind of bonds you see. Critical thinking questions. meant to mention, I don't have your exams created yet, so that's probably pretty obvious by now. We are halfway done. Maybe we should let's talk about the answers. I just need to give you some time to digest some of this yourself without having to just listen to me. So really quickly, these questions, 3 different bond orders, you know, you go through them, there's a whole bunch of 1, bunch of 2, a few 3. So if we focus on the really simple ones, like 3 here, that's a bond order of 3, that's a bond order of 3, the carbon-carbon bond. Bond order 2 is the carbon-oxygen here, double bond. Bond order of 1 is like a carbon-carbon single bond. So any examples work. And then the idea is, what is the relationship between bond order and number of electrons, which is similar to question 4. What is the relationship between bond order and the designation of single, double, or triple bond? So that's pretty much it. The bond order is the same as whether it's single or double or triple bond. So a single bond is something with a bond order of 1 is sharing 2 electrons between the 2 atoms. Something with a bond order of 2 is sharing 4 electrons, double. And then something with a bond order of 3 is sharing 6 electrons. 3 sets of 2. You might ask, why do we have this thing called bond order when it's easier to say single bond, double bond, triple bond? There's fractions too. We're going to eventually see fractional bond orders. So how do you draw a 1.5 bond? Like that? How is that a 1.5? What about 1 1/3? You know, you get weird fractions like this. So you can't do that with a Lewis structure. You have to describe bond order with simple numbers. So that's why we have bond order still. Yeah.
I was going to say, do you just, I don't know if this applies here, but do you just multiply it by like a number, and like if you do that in a reaction equation, do you multiply it if it's like a 1.5 or something?
Well, the bond order is going to come, so the Lewis structures we've seen have been pretty normal. They've been like a single bond or a double bond if you just share electrons. In rare cases, a triple bond. We're going to eventually see the bond orders of 1.5 and fractional bond orders when we study something called resonance. And this is an idea that electrons are not fixed in position. And we're going to see that. So instead of having the electrons stuck between the carbon atoms, in some cases the electrons can move around the molecule. But we'll come to that in a little bit. All right, what's left? So rank the types of bonds in order of increasing bond energy. So this is hopefully obvious. Single bonds have kind of lowish energies. Double bonds have higher energies. Triple bonds have the highest energies. Okay? So the next part is important as well. So anything that has a higher bond energy, we consider it a stronger bond. Because if you think about it, when something has a high bond energy, it takes a lot of energy to break it. The more energy it takes to break it, the stronger the bond is. So that's what bond energy is, the energy it required to break that bond. So the higher that number is, the stronger that bond is. So here's another table, slightly different than the first one. And we're going to answer questions based on it here. Consider the series, what is the bond order, what is the trend in energy, and what trend would you predict for the size? So let's do the first two, which is bond order and bond energy. And, you know, I think this is not hard to see. You look at HF, HCl, HBr, HI. Look at the bond energy is going down as you go down the periodic table from F to I. I think that was it, right? Just bond energy. What was it? Oh, bond order. Yeah, they're all bond order 1. They're all single bonds. But the bond energy is going down. So let's talk about size now. So what do we think the size of the bond is going to be? Well, I think we briefly looked at how to think about the size of a bond for a covalent bond. We kind of focused on ionic stuff earlier. But you know, what you're basically doing is you're taking the two atoms and you're taking the center of one atom, the center of the other atom, and measuring the distance between the two centers. That's how you measure the bond length. Now, kind of to explain or to kind of predict it, we're going to look at the relative sizes of these atoms. Hydrogens are always pretty small, so let's draw a little tiny bubble here. And let's compare fluorine with iodine, for instance. So fluorine is going to be pretty small as well. A little bit bigger than hydrogen, but still pretty small. And I know they should be overlapping because this is a covalent bond, but let's just do like that for now. But if we compare fluorine with iodine, I'll try to get hydrogen the same, we know that iodine is a much bigger atom on the periodic table because it's got electrons all the way out to shell 5. So let's just exaggerate it and draw it really big. And now if we consider, well, what's the bond length? Well, it's center to center. So there's the bond length for HF, and then for HI, it's a lot bigger. So we should expect to see HI get longer. Or as we go down the periodic table on the halogens, the bond length will get longer and longer and longer, which I think the video already kind of spoiled. But okay, so that's kind of what we're doing in question 6C. We're going to do the same kind of reasoning for question 7, except instead of HF and HCl, we're looking at Cl, Cl, and Br, Br, and II. So what's the bond order? There they are. Here's the 3. All bond order 1. And the bond strength, no surprise, as you go from chlorine down the periodic table to iodine, the bond strength weakens, just like it did with the HF all the way to HI. And in terms of size, the same explanation as the one we did over there. And a Cl-Cl bond is going to be smaller than a Br-Br bond, and II bond is going to be the biggest. Okay? Now, I think the next question is the most interesting. Which of the following statements appears to be true? The longer the bond, the stronger the bond, or the shorter the bond, the stronger the bond? So, as you go down the periodic table on the halogen side, the bonds get weaker, but they get longer. So the shorter they are, the stronger the bonds are. And this observation is actually true. In general, the shorter a bond is, the stronger it's going to be. Okay? So it's B. The shorter the bond, the stronger the bond. The longer the bond, the weaker the bond. And then in general, number 9 is kind of a summary of like the bond energies. I'm not going to say you should memorize this range, but just kind of get comfortable with thinking about it. So if we go back to table 1 and look at these bond energies. Actually, let me just switch to this. That's even easier. All of the single bonds, I mean, they vary a little bit, but none of them are above 500. Maybe that one, 550. That's like the highest I've seen it get. But everything's under 550. All single bonds are under 550. Whereas double bonds are somewhere 700 to 800. If you look at any bond order 2, that one's 804, barely 800, okay? 700 to 800 or so. And then triple bonds are pretty much over 900. So that's generally how you should think of these bonds. So triple bonds are always going to be stronger. They're high energy. Double bonds are kind of strong. Single bonds are the weakest. They have the biggest variability. But, and this is where we get to the last question. The most important determinant of bond strength is bond order. If the bond orders are the same, the shorter the bond, the stronger the bond. So this is a true statement, and the idea behind this is look at the energies involved between bond order. They were huge, right? So single bonds ranged quite a bit, from anything to 500 or so. Double bonds jumped up a lot. But if we looked at just between single bonds, you know, the energy ranged from 500 or so to 300 or so. And then here it's just 100 to 200 something. So the biggest factor of bond strength is first a bond order. First look if it's double, single, triple. And then you can look, okay, well if they're all single, then we can compare the length of the bond. Then we can compare, is it an HF bond or is it an HI bond? You know, so HF is going to be shorter, so that's going to be stronger. So basically look at bond order first, and then you can look at, you know, the length of the bond, whether it's longer or shorter based on the atoms that are connected. Hopefully that makes sense. So it's kind of like Coulomb's law. We kind of prioritize the charge. That was the most important thing. And then after that, distance mattered. Here, in this case, order is the most important, bond order. Then you can look at what's connected. Okay. So far, so good? We can skip that one. So HF is the strongest bond. Why? Because it's the shortest. But for this one, which one is the longest? Okay, sorry. So, longest bond. Excellent. Everybody knows it's the single bond. Next, which is easiest to break? Hopefully this is just as easy. All right, we've got answers. And, oh, okay, somebody said C. So, it is going to be still A, all right? The single bond only has 2 electrons holding those 2 atoms together. Versus a triple bond has 6 electrons holding everything together. And we saw that triple bonds have a higher bond energy. It takes a lot more energy to break them. So single bonds are always going to be easier to break. And I won't turn it on to the last one, but which one is the strongest bond? So single bond is the weakest bond. The strongest bond is going to be C, okay, triple bonds. Okay. And this is not applicable, but what is the bond order? 1, 2, 3. Okay? Okay. This is not too surprising. Yeah.
So to say bond order, like when you do CO2 or some complex atom, you say bond order is based on the highest.
Yeah, you have to be specific about which bond you're talking about.
Okay.
Bond order is always for one bond.
Okay,
Yeah.
cool.
That's a good question. Okay. Ignore my little ink that I never erased. But here is a nice little graphic that shows you the difference between real molecules and bond order and strength and their length. So on the left, you've got oxygen, the stuff we breathe to live. Ignore that. But down here, it's a double bond. Bond length is 121 picometers. The bond strength is not super high, but high, around 500. This is hydrogen peroxide. This has an oxygen-oxygen bond in it, just like oxygen does, the element. But it's a single bond. And notice that it's longer and it's weaker. And this is why it's so reactive. We use hydrogen peroxide to clean blood out of things. It reacts with blood and gets rid of the iron red colors and stuff like that. We use peroxide for lots of things. Over here, some of you guys had this in your lab. This is nitrogen. This is also something we breathe. This is what the majority of air has in it. Doesn't do anything for us, but it's a triple bond. Very strong bond. It's inert. Generally, it's not completely inert, but it doesn't really do anything to us. Just breathe it back out. This stuff is rocket fuel. It's got a much longer bond. It's much weaker. It's so easy to react with it. It's easy to break. In fact, airbags have this inside them. There's a tiny little glass ampule, which basically just means a sealed glass container. When you're in an accident, there's a mechanism that breaks open the glass container, and it reacts. There's some other chemical there that reacts so fast that it creates all this air, which makes a little mini explosion. Not air, gas. It makes a little mini explosion, which inflates the airbag. So you're actually doing a little explosion in your face. Yeah.
Is that why it burns you a little bit?
I'm not sure. It's possible. I feel like the burns must be friction burns.
Yeah.
Like the material in the bag is like canvasy, I think. It's well measured out. Like it's just enough to inflate it. If it was more than that, it would blow. It would pop the bag and it would cause severe damage to your face. But yeah, it's a little mini explosion, contained explosion in an airbag, which is why you can't reuse them. Once they're blown, that's it. This is not something self-serve. You have to just get it from the factory. Yeah.
So why don't they use like triple bond nitrogen in jet fuel instead of the single bond? It seems like the triple bond would have more energy.
Because it's hard to break.
Okay.
It's extremely difficult to break. Which is why I say it's generally inert. It doesn't really react with anything. In fact, even oxygen is considered less reactive. So if you're a car person, what gas can you hook up to your car that will make your car fast immediately? Nitrous. Nitrous looks like this. That's what nitrous oxide is. Notice that bond is, you can cut that easily. Suddenly you have free oxygen available to burn in your gasoline. That's easier to break than O2 is. So that's why nitrous works so well for like boosting your car's power. Just because that O comes off so easily. Some of you might have drawn it this way. But if you do formal charges, you'll notice that this is better. This is the minus on the O instead of the minus on the end. Anyway. Okay. But that being said, you do make reactions with this. Nitrox is like the category, or the name given to a category of gases formed in your automobile engine when there's inefficient combustion. makes NO2, and that makes smog. So you have your catalytic converter that breaks down NO2 into plain N2 again. So you can react with N2, it's just very inefficient. So it's not for combustion.
Okay.
Yeah. Okay, so we did bond order. Here's a nice little table in case you need a review. And again, bond energy, it goes up this way, even though the arrow's pointing down. It's going up towards this way. So triple bonds have the highest bond energy. It's not the best slide, but it works. Okay. So, I guess here's more examples. So hydrogen's bond order of 1, carbon dioxide, each bond in there has a bond order of 2, and nitrogen, the gas, is a bond order of 3. Here are some bond energies for those bonds. We talked about lone pairs in labs, so I'm going to skip that as well. Okay, so here's the new stuff. We're going to talk about electronegativity, but before we can talk about electronegativity, we're going to talk about something called average valence electron energy. But before we can talk about that, let's go back to photoelectron spectra data. This is data you've seen before. And we're going to eventually use it to calculate what is called, so the average valence electron energy. This is an average ionization energy for any of the valence electrons. So what I mean by that is, if I were to ionize potassium, right, here's potassium, the ionization energy from potassium is always the easiest to remove electron, right? This one right here, which is in the 4s subshell. That's the easiest to remove one. The ionization energy of potassium is 0.42. But what if I have something like silicon? So it's got electrons. The valence electrons are the 3s and the 3p valence electrons. Well, the ionization energy is still 0.79, the easiest to remove electron. But like, we don't want to make it that simple anymore. When we're dealing with covalent bonds, all of the valence electrons are involved. So we have to include these as well. So how do we combine these two numbers into a number that we can use as an average valence electron energy? And that's what we're going to calculate next. So let's start with CTQ question 1 and 2 on connectivity 19. We're skipping a whole bunch of stuff, which we'll come back to a little bit. 274, 275. So this is like the intro thing. We're going to keep going next. Just want to make sure everything makes sense. Because we're going to start thinking of weird numbers next. mostly done. Hopefully this wasn't hard, because we're just trying to get you back into thinking about these kind of energies again. So we have one valence electron in hydrogen. What is the average ionization energy of one valence electron in hydrogen? What is it?
1.3.
It's, yeah, there's only one, so that's the average, 1.31. When I do helium, what's the average?
2.37.
Yeah, if they're two electrons, they're both 2.37. Now we're not talking about removing one then the other. We're removing one or removing the other. Either one is 2.37. Okay. So that's not so hard. So which holds valence electrons more tightly? Helium, because the ionization energy is higher, or the average valence electron energy is higher. So now we do beryllium. So what is the electron configuration? 1s2, 2s2. What is the average ionization energy for valence electrons in beryllium? There it is. So only 0.9, right? That's the valence electron. That's where the valence electrons are. They're in the 2s. And they're both 0.9. So 0.9. What is the electron configuration for carbon? This is beryllium. For carbon, 2p2. And if we look up what the valence energies, ionization energies for those valence electrons, well, let's show the header there. For the 2s, it's 1.72. So these are the valence, right? Ignore the inner shell electrons. But for these, it's 1.72. And for these, it's 1.09. So now we have two different numbers. But for now, it's not a big deal. Is the average ionization energy for the valence electrons in carbon greater than or less than that for beryllium? So beryllium was what, 1.09, no, 0.92. I think that's what it was. Let me make sure. 0.9, not 0.92. So, is the average valence electron energy for carbon higher or lower without doing any calculations? It's higher. I mean, we're going to average these somehow, but these are all higher than this number. So whatever they average out to, it's going to be higher than this number. So carbon's is higher, no matter what. So, oh, I guess we could just go to this. So, let's see that. So how is average valence electron energy actually determined? And the connectivity kind of steps you through that if you want to read the following sections. But I'll show you. So we're going to do it for phosphorus. And for phosphorus, I'm going to write down this electron configuration, then I'm going to switch back to the chart. So phosphorus is neon core, 3s2, 3. I should know this. 3p3. If I switch to the table, there's phosphorus right there in near the bottom. We only care about these, the valence energies, and the 3s are 1.95, and the 3p's are 1.06. So the point of how to calculate an average is you just basically need to add up the energies of each electron and divide by the total number of electrons. That's it. So there are 2 electrons in the 3s. So the first electron has this energy. The second electron has that same energy. There are 3 electrons in the 3p. The first one has 1.06, the second one is 1.06, and the third one is 1.06. And this is an average. So you add up all those numbers, you divide by the total. There's 5 electrons. And this will give you the average valence electron energy. It's as simple as that. It's, nothing, no magical formula, just an average calculation. You just need to know what to plug in. 1.06. 95 plus 1.06 plus 1.06 plus 1.06 divided by 5 is 1.416, which rounds to 1.42. These are in megajoules per mole, so it's still in megajoules per mole. That is the average. So now we have this number we can use for either the s or the p electrons as an average. So basically we can compare a big range of elements. So so there it is. They just did it a little simpler than I did. They did 2 times 1.95 and 3 times 1.06 divided by 5. I think mine is probably easier to see. But that's it. That's how they calculate it. So these are, and here's my phosphorus, 1.42 exactly, there he is. These are average valence electron energies for various elements. So I think they included a couple transition metals here, but for the most part they're missing. And there's a trend to look at, but let's just go straight to problems 3 and 5, page 276, and just kind of answer those questions. Make sure. So what are we going to use average valence electron energy for? What does it do for us? This is a tool. We're inventing another tool for comparing elements. So for 3 and 4, it might be better to say use the shell model of atoms or the concept of core charge. Same for 4, or. One of them is better than the other for each example. Nobody's gonna say yes.
You know
Even
what?
if they
I
do.
wanna quit.
Yeah.
Just as bad, you know. Dad gave me the Samus t-shirt.
Yeah.
Never played Metroid myself. Admit.
Oh my god, this is like my childhood. Original Resident.
Yeah, it was a bit later than that one. Original Xbox was a relic to me.
When you beat the game as a kid, and like nobody had the internet, so word wasn't spread other than through Nintendo Power. You find out that it's a woman in there, like oh my god, it was like mind blowing. Because it's all in a helmet the whole time. So.
Your masculine heroine can be bad.
It's a good game.
Groundbreaking. Always was our favorite.
There's a silly movie on Netflix that is told kind of like Princess Bride. There's somebody narrating to their daughter, Doogie Howser, or what is his name, Patrick Harris. It's about Nintendo getting the first Nintendo in the neighborhood. It's a pretty funny movie.
What's that called?
8-bit something. I forgot. It's a family movie. It's amusing. All right. Okay. Oh yeah, we're ready. So this shouldn't be a stretch. The same arguments we use to explain the increase of ionization energy as you go left to right and the decrease of ionization energy as you go left to right exactly works for these, because what AVE is kind of ionization energy, but we're including the S electrons too. No, so not just the P's, which is the easier to remove, but we're including the S. So it's almost the same. So for 3, you would want to use core charge, left to right. So if you compare sodium to chlorine, the core charge of sodium is +1. It's got a single electron. The core charge of chlorine is a +7. It's got 7, 3, 4, 5, 6, 7. And, you know, the idea is, well, why does this have a higher average valence electron energy? As you can see it right here in the chart, 1.59 versus 0.5. Well, it's because these electrons are being held on with a +7 core charge. So they're harder to remove. And we're not just looking at the P subshell, but the S, all of them together. So that works. And then for in a group, excuse me, going up and down, you can compare sodium with well, no, let's not do sodium. Let's do lithium, because that's easier to draw. Let's do lithium with potassium. Why not? That's a terrible LiK. So +3 nuclear charge. We're going to do this the shell model here. So you've got your first shell, you get your second shell. There's lithium. Potassium is going to be +19, excuse me. And it's got the first shell, the second shell, the third shell, and even the fourth shell. So that's got 2, that's got 8. 1, 2, 3, 4, 5, 6, 7, yeah, okay. 8 here. And then 1 here. So why is potassium's average valence electron energy lower than sodium or lithium's? That electron is further away. They both have the same core charge, they're both +1 core charge. But this one's further away, so further away means less attracted. It's easier to remove. Same explanation we use for ionization energy, so it works. And that's because AVEE is just tied to ionization energy a little bit. So we can use the same explanation. So let's explain why Na is more likely to form Na+ than O is to form O+. So it costs this much energy to remove one of the valence electrons for O. but it costs this much energy to remove one of the electrons for Na. This is easier to form Na+. It's easier to remove an electron here than it is from here. Okay. Now you might be thinking, this seems redundant. We've studied something similar to this. Why are we learning this? Well, again, we're combining all of the valence electrons. We're not just looking at the easiest to remove one. We're combining them all together into one number. And, well, let me get, before I get to that, no, we don't need to do this. So if you look at this, which of these electrons is held more tightly? The one with the highest AVEE is held more tightly, so bromine. The trend, we see in the trend, it increases across a row, decreases down the column. So, I guess here's the reason we're studying this. So, we can use AVEE. It's a useful number to solve for. We can compare all of the elements of the periodic table, and we can see that metals tend to have an AVEE that is less than 1.06. Don't memorize that number. Don't worry about it. Non-metals tend to have AVEEs at greater than 1.26, and some metals tend to be somewhere in the middle. That's why they're both metallic and non-metallic properties. But greater than that is this tie to a concept called electronegativity. So we're going to switch gears for a second. We're going to come back to AVE in a second. But electronegativity, as we've learned in lab, is defined as the ability of an atom to attract shared electrons. So we're talking about covalently bonded electrons, so electrons that are being shared between two atoms. One atom might have a greater electronegativity than another in the bond and attract those electrons to itself more. So it turns out that this electronegativity, and this is an important concept to understand in all of chemistry, honestly, that you can measure an electronegativity, or I should say calculate it, using something like AVEE. So first, electronegativity is not measured. It's always a calculated thing. It's a made-up thing. It's a made-up number that's based on a lot of different things. There are actually 15 different electronegativity tables. So it really depends on how that person who made that table calculated the electronegativity. There's a lot of different ways to do it. The most famous one is the Linus Pauling table, which I'll show you in a second. He's a biochemist, or I think he's a biochemist. He got a Nobel Prize twice, once for chemistry and once for peace. Anyway, these numbers, these we have for electronegativity, they are relative, meaning they have no units. They are kind of, like I said, it's a tool that we use to kind of gauge whether something is more or less electronegativity. What does that mean? Do they attract shared electrons well or not? So, given that, one of the ways to calculate an electronegativity is to use average valence electron energy. And most electronegativity scales, tables, are scaled to up to 4. Like 4 is the highest, approximately 4. And then around, just above 0 is the lowest. So to get that scale, if you multiply AVE by 1.8, you get a good value of an electronegativity. This is one way to get electronegativity. So I'll mention that there's a table of electronegativities in your connectivity workbooks. I think it's in the appendix. That one is not a standard table. It is only to be used for your worksheets, workbook things. I believe they get it using average valence electron energy. And one of the ways I can tell that it's not standard is fluorine is like 4.1 something. In most tables you're going to see fluorine is exactly 4. So it really, like I said, it depends on which table you're looking at. They're all a little different. So for any of the activities that you have to calculate using electronegativity, use the table from your workbook. For Mastering Chemistry, do not use that table in your workbook. Use the one that you're going to see next. So, what is the periodic trend for electronegativity? It's the same for AVEE, okay? Notice how we got it. We just multiplied it by 1.8. That's it. So it increases across a row, and decrease is going down a column. So here is the Linus Pauling version. Notice that fluorine is exactly 4, and there's no noble gases. And that's because generally, and you guys saw an example that bucked that trend, but generally we don't make compounds with noble gases. So it really isn't, it doesn't, again, what is the definition of electronegativity? It's ability to attract shared electrons. It doesn't make sense to include noble gases in most of these tables. So 4 is the highest, and then as we go down here, we get to the lowest. You don't have to memorize any of these numbers. Don't memorize them. Memorize the trend. The only thing I would memorize is in your head, know where hydrogen sits. So this 2.1 means it's kind of right here, between boron and carbon. Okay? That's the only thing I would try to remember, to keep straight in your head, because it's a way to. But the numbers themselves, don't worry about the numbers. Okay? If you need the numbers, you'll have the table. So know the trend and know approximately where hydrogen is. And here they're showing you hydrogen kind of where it belongs. There you go. And even these trends aren't perfect. The transition metals always throw a wrench in things. But if you look at the main group stuff, it's pretty good. Mostly good. So, let's show you this video. And I'm going to fast forward. This is most of it. And for some reason, we saw some terrible commercials. So, yesterday, oh my god, it was terrible. It was.
What if you could get rid of your kitchen garbage at the push of a button?
There's a guy selling a beanie.
Hey, I'm Matt from Pila, and I want to introduce you to my friend Lauren. At Pila, we're
Humans, like chemicals, are really all about bonds. Think about all the relationships in your life. You're a cat. One relaxes. Negative 239 molecule, they actually spend the majority of their time in the space between them. This is often described as sharing electrons, and we call this kind of bond a covalent bond. But not all sharing is equal. As you know, I have an older brother. The strength with which an atom holds shared electrons is called its electronegativity. The electronegativity of various elements are all super well known and waiting for you in tables on the internet. If two atoms in a bond have very different electronegativities, like say hydrogen at 2.1 and oxygen at 3.5, the electrons are more attracted to the atom with the higher electronegativity. The difference is so great that the electrons spend most of their time around the stronger atom and much less time around the other one. Like how all of the neighborhood kids wanted to hang out with John, my older brother, because he was more charismatic. When the electrons hang out closer to one side of the bond, it creates a slight negative charge in that area and a slight positive charge around the other atom. This separation of charges is called polarity. And it's the polarity of the molecule that these atoms form, H2O, that makes water the most important molecule on Earth. Covalent bonds like this, where electrons are attracted to one atom more than the other, causing a separation of charges, are called polar covalent bonds. But when a covalent bond forms between two identical atoms, like the two chlorine atoms in our graph earlier, the electrons are distributed evenly. We call this a nonpolar covalent bond. But you've also got to consider the middle option, where the atoms aren't identical but have very similar electronegativities, like hydrogen with an electronegativity of 2.1 and sulfur at 2.5. The difference here is so tiny that the electrons are pretty much still evenly distributed, and we call that a nonpolar covalent bond as well. There's a huge world of important chemicals that have these kinds of bonds, so many in fact that we will dedicate a couple of separate episodes to them. Covalent bonds tend to form from nonmetals and sometimes metalloids, those elements that have both metallic and non-metallic characteristics. That's because most of them hold their Alright.
This keeps going, and these videos are decent, so if you ever want to look like, these are like crash course stuff, yeah, they work pretty well for getting ready. So, the lead into that is important. The electronegativity is going to let us figure out whether a covalent bond that we're looking at is going to be polar or nonpolar. And that's because there is not an even sharing of electrons, like we're like normally assume. So let's go to page 277, 278, do 6 through 10, and I think this is how this is, but let's go through that real quick. 77. And yeah, you're going to be using not this one. Although you could use this one, it would just get different numbers. Yeah, notice the fluorine here. It's not 4. Plus they've got the noble gases. Anyway. All right. I think people have gotten it. So this is really just a pause to make sure you're looking and seeing the same things I'm saying. But 6, describe the trends. So you see them, right? Left to right goes up, top to bottom goes down. And it matches first ionization energy. You know, they move the same way. And I saw everybody pull out their calculators, so I know you guys are doing 9. This ratio, it changes a little bit, but it's approximately 1.8. The whole thing, right? It's a little higher, a little lower in some cases, but it's basically about 1.8. So basically, we're just proving to you that this concept, this way of getting electronegativity, it's similar to average valence electron energy. So the way we're thinking about electronegativity works. It's related. All right, let's see what's next. So let's get to this polar, non-polar stuff. This is actually the hardest thing, I think, for students. Because to really understand it, you have to visualize in 3D in your head. I have shortcuts to get around that. But let's get through this first. So covalent bonds, they can be polar, they can be non-polar. So nonpolar bonds are where the electrons in the covalent bond are shared evenly. And that's the case when your atoms are the same, fluorine, fluorine. Think of it like a tug of war. It's an equal tug of war. That flag in the middle of the rope isn't moving. And I think a Squid Game for some reason. All right. Hopefully everybody's seen that. Okay. So a polar covalent bond is when you have uneven sharing. And what's frustrating about this is, on the video you saw what happens if your elements are different in electronegativity but still close. And the frustrating part is, well, what's close and what's not? And that really is kind of, it depends. That's the best thing I can say. So I'll try to give you a boundary, but it's not a perfect boundary. Like here, this is when it stops being polar and is nonpolar. There's no clear boundary. So you're going to see this a lot. Let me go back to these pictures here. These pictures are simulations. They're computer calculations of what are called the electrostatic potential. So all that we're doing with the computer is calculating where the electrons are most likely to be. And so after that, what they do is they paint the regions where you're most likely to find like negative electron density. And then, so that's the red area, and then the blue areas are where it's more positive, so less electron density. And if it's even on both sides, then you can't say that one side of a molecule or the other side is more negative or more positive. So even though there's red and red, it's even. There's no positive side, there's no negative side. This is a non-polar. But in this molecule, there's a red side and then there's a blue side. That's a polar molecule. We'll often, so you don't have to draw this. This is a computer thing. What you'll often see is, first of all, these symbols here. This is a lowercase delta. So the same as the capital triangle delta, but it's a lowercase. And delta in chemistry often means partial. So not a full number one, but it's a fraction. That's kind of what it means, a partial charge. So this means partial positive charge, partial negative charge. Undefined how much, like whether it's 0.1, 0.2, even smaller, even bigger, it's undefined. It just means partial, that's all it means. The other thing you'll see is an arrow, and this is called a dipole arrow. It points towards the negative side. And if you notice the tail has a little plus sign on the tail. So that's another reminder that the tail is the positive side. And so the arrow points towards the side that is negative, and the tail is on the positive side. So that's a dipole moment. And if you have done any kind of linear algebra or vector calculus, if you've done vectors at all in math, that's a vector. So it's got magnitude and direction. But if you don't understand that, don't worry about it. We're not going to make it that complicated. So, just to remind you that we don't say ionic bonds are polar or nonpolar because they are completely different kinds of bonds. These are only for covalent bonds, okay? So, partial charge. So the idea is electrons like to hang around the atom that has the higher electronegativity. That's what En means. You can also think of it as greater average valence electron energy too. It's similar numbers, I guess. But we're going to talk in terms of electronegativity from now on, okay? And so the partial negative is always going to be on the side that is more electronegative. In this case, it's the bromine. The partial positive is going to be on the side that is less electronegative. It's the hydrogen. So you'd have to look at the numbers to see, because it's hard to see where they are. Again, fluorine is the most electronegative, but if you saw a chart, I think bromine is 3.0 and hydrogen is still 2.1. So 3.0 is higher electronegativity. The bromine is going to have the partial negative charge. And if you do the dipole moment arrow, the arrow will point towards the negative side. Technically, the length of your arrow defines how polar it is. The longer it is, the more polar it is. The shorter it is, the less polar it is. We're not going to worry about that, though, okay? So, there we go, the one with the partial negative charge is the one with more electron density around it. The electrons hang around that side more often. Again, we're Heisenberg's uncertainty principle. We don't know exactly where the electrons are, but we know the electrons tend to hang around that side more. Yeah, and it's the side with the greater average valence electron energy, the ability to hold the electrons more tightly. So here is lithium hydride. And just by looking at this picture of lithium hydride, would the partial charge of hydrogen be negative or positive? Was it a partial negative or a partial positive on the hydrogen itself? And the hydrogen's on this side. So that's lithium, that's hydrogen.
Wait, which side is lithium? Lithium's on the right.
So it's written the same way it's drawn. Lithium's on the left.
Oh, I see. I see.
Yeah. So you can either look at this picture, or you can actually look at a table of electronegativities. And so look at the electronegativity for lithium. Look at the electronegativity for hydrogen. And which one is the higher electronegativity? So the higher electronegativity is going to get the partial negative charge. So in this case, the answer is A, okay? So going by the picture, the more reddish, this is electrostatic potential, the more reddish side is going to be the more, where the electrons hang around more often. And so if the electrons are hanging around the hydrogen side more often, the hydrogen is going to pick up a partial negative. Right? Electrons are negatively charged. If they hang around that side more often, that side is going to have a partial negative charge to it. This side is then going to have a partial positive charge as a result. So the hydrogen, the partial charge on hydrogen is negative. And again, I say partial. It's not a full -1. It's not an ion. It's not an ionic bond yet. It's still a covalent bond. Here's H2. And the partial charge on hydrogen would be what in this case? So, in this case, there's two hydrogens in there, and they are equal. So I think maybe people saw, oh, it's green, so it's closer to the positive side. But again, even if you think of it as positive, you have to look at the picture. Is there one side that's more positive and one side that's more negative? That's the only way it's going to be polar. But if there's no clear side, hey, this side is positive, this side is negative, if you can't see that anywhere, it's not polar at all. It's going to be non-polar. So in this case, there is no partial charge. In fact, the two hydrogens have the same electronegativity. They're going to share those electrons completely equally because they're the same atom, the same element. Okay. And then finally, here's HF. The partial charge of the hydrogen in this case is what? You can see now, hey, one side is blue, one side is red, one side is partial positive, one side is partial negative. And, so the hydrogen side is on the left. So the hydrogen side is the partial negative. Partial positive, excuse me, positive. How do we know that without looking at the picture? Again, look at the electronegativity table. Fluorine is more electronegative than hydrogen is. So fluorine, the more electronegative atom, is going to have the partial negative charge. The electrons will hang around the fluorine more often. And that means the hydrogen will pick up a partial positive as a result. Okay. So this is these three slides was a unique set of slides because this is one case where one element, hydrogen, can be all three, positive, negative, or neutral. In most cases, it's pretty clear. Usually the halogens are negative, but it's not always clear. So pay attention to what is in the bond. Compare the two atoms that you're bonded together, and one of them will be more electronegative or not. And And that's how you figure it out. So there we go. Here are the actual values for electronegativity. For lithium is 1, hydrogen is 2.1, fluorine is 4. So again, compare them. For the first one, the electrons will hang around the hydrogen since it's more electronegative. In this one, the electrons will hang around the fluorine since it's more electronegative. And for this one, since it's the same electronegativity for both atoms, it's equal. Tug of war. Nobody's going anywhere. So here's a picture of the halogens, HF, HCl, HBr, and HI. So hopefully you can see a clear picture as this is very polar. There's a clear partial negative, clear partial positive. It's very red, very blue. But as you switch fluorine to bigger halogens, it's not as clear that there's a positive and negative side. I mean, yes, you see this distortion. This is bigger, that's smaller, but like it's green and green. It's not as clear. It's less polar. It's approaching non-polar. And the reason for that is, look at the difference in electronegativity between hydrogen and fluorine. So basically we took the two numbers, one for hydrogen, one for fluorine, and we subtracted them. And the difference, that subtraction, is this number. So there's a huge difference between hydrogen and fluorine. But then hydrogen and chlorine, there's smaller difference, smaller difference. When we get to hydrogen and iodine, the difference is really small. We're approaching something we could call almost non-polar. So when you get to that small 0.3, 0.4, anything less than that, that's pretty much non-polar. Okay. Yeah. So as the difference in electron pull between the two atoms decreases, the electron density moves back to being concentrated between the atoms, becoming less polar. So HI has very equal sharing of electrons. Not completely, but pretty close. Yeah, so here's I 2.5 and H 2.1. So if that was pretty much nonpolar, look at carbon and hydrogen. Carbon is 2.5, hydrogen is 2.1. Yes, there's a small difference, but it's really small. And in fact, whenever you see these long hydrocarbons, so like, we've drawn these very tedious, long carbon hydrogen compounds. There's a lot of covalent bonds in here, but they're all kind of nonpolar. So in fact, this thing is kind of nonpolar. So we consider hydrocarbon bonds very nonpolar. It's only when you throw in oxygen and chlorine or bromine or something like that, that's when it starts getting polar. Yeah. Nitrogen. Okay? So, yeah. Crude oil, very nonpolar stuff generally. Okay, so here's some actual numbers of the partial charge, just in case you were curious. So HF, which is one of their most polar covalent bonds, like if you actually measured what the charge was on the hydrogen and the fluorine, it's not that high. It's kind of high. It's about a third of a charge. So it's not a full -1 or a full +1. If it was, it would be ionic. But it's a fraction of a charge. But then when we get to HBr, it's really small amount of charge. So it's just to give you an idea of what those partial charges are. And that's why we just say partial. We don't worry about the actual numbers. Okay? So the one thing to keep in mind is when you look at all these partial charges, they have to balance out to 0 when you're talking about a neutral molecule, right? Neutral molecules have no charge overall, so there shouldn't be any imbalance. So whatever the charge of one side is, has to be opposite for the other side. So HF, the hydrogen side is plus 0.29, the fluorine side is minus 0.29. Balances out. Okay, so this dipole arrow that we drew, I mean, I told you it was kind of a decoration, but it's not really. It's based on a measurement, like, so you can measure how strong this dipole is. And we will do this in next week's lab. They use a really funny unit called the debye. That's the unit we use. and like I said, the strength of that dipole is proportional to the size of this arrow. The bigger the dipole moment, the bigger the arrow is going to be. And we call it a dipole because there's two poles. There's a positive side and there's a negative side. That's it. That's where the word comes from. Again, draw the arrow towards the negative side. The tail of the arrow, we put a little plus on it just to identify it as a dipole moment. And it's always on the positive side. Okay. So the variable that we use for dipole moment, if you put it in the equation, we use mu. And again, this is something we can actually measure, although you're not going to worry about it too much. So the greater the dipole moment, the more polar that bond is. There it is. Here's the Debye unit. So the dipole moment for HCl is 1.11 Debye. Don't worry about the numbers. I'm just telling you that we have a way to measure this if we wanted to. And you will calculate this in computer simulations next week. Next week's lab is we're going to take our understanding of shapes of molecules and Lewis structures and whether a molecule is polar or not, and apply that to understanding global warming, like what makes a gas a global warming gas. So it's interesting. Oh, is that it? We're ending early. All right, I don't want to go any further than this because I don't want to overload you. But let's put it this way. Thursday, we'll talk more about how to figure out whether a molecule is polar or not. Because right now we've been looking at polar bonds, just one bond at a time. Right? I think that's not hard to do. You look at the electronegativities of the two atoms in that one bond, and whichever one has the greater electronegativity, that's going to have the partial negative charge. The other one can have the partial positive charge. We will have to expand that idea into a whole molecule. So what if you have a molecule that has 4 bonds in it? How do you compare them? How do you put them all together and say, oh, the whole molecule is polar or nonpolar? Because you can have a nonpolar molecule that has polar bonds. And you can have polar molecules that have polar bonds. So we'll talk about that on Thursday. I don't want to start that yet. So that's it. That's it for today. Any questions? You can just take off early. Up to you. I'll try to get your labs or your exams done, give them back to you on Thursday. Definitely by Thursday. I'm hoping to get it by tomorrow, but definitely by Thursday. So I got a big block of time Thursday morning. I can do it too. All right.
How do you end a polar and political conversation with a chemist?
Did you just make that up, or did you?
Yeah.
Oh wow. It's bad, but it's not bad.
It's bad.
It's not terrible.
Sure, I can never guarantee funny jokes, but I can guarantee jokes.
Most chemistry jokes are horrible. I hate repeating them. They're so bad.
Yeah, but it's so it's so fun to think of your own.
Yeah.
There's one
Block jokes are really good too.
Was that?
I said block jokes are really good too. They're long.
Very quickly.
Okay. So, I think instead of using kind of like a picture of the periodic table, we want you to kind of illustrate in your head how do you see kind of the electron moving from one thing to the other. So you'll have to compare like a couple different ones, but like if you take, for instance, chlorine or chloride, and then chlorine, where does it get the electron from to become chloride? And then like show, it's getting it from an iodide maybe, and it's stealing that electron from iodide and adding it to its shell to make chloride, and the iodide is going back to iodine. Does that kind of make sense?
Yeah.
Okay.
Chloride.
Okay.
And then for this one, what are they asking? Are they asking to explain the trend of the reactivity?
So, so first, give a hypothesis that explains your claim for reactivity trends in the helicopter. So you say that, let's see. Well, okay. One second. Trying to link it to this. Oh, this is this one. Okay. So this is here. So
This is the claim.
yeah, this is the claim. You are saying that reactivity increase is going down the group. So before I go to that, let me fix this because let's see, you don't have to hold that here. So when we talk about reactivity, we're not talking about reactivity of these. We're talking about reactivity of these. So which ones of these tended to take an electron from something else? Well, did it? Because you're saying, so in the end, mostly you had I2 left.
I thought that's what that was.
Well, so the fact that there's I2 left means that I2 is
didn't-
not doing anything. It's the one getting electrons stolen from.
Oh.
So which one is never here?
Oh,
Is
C-
chlorine.
Yeah.
And that's because Cl2, as soon as it has anywhere to take electrons from, it'll do it. And it'll make chloride. So chlorine is the most reactive.
Okay.
And then,
Oh yeah, because ionization energy. I literally wrote this like as soon as ionization energy decreases secretome. So
yeah, so
it's more reactive to secretome.
once chlorine gets that, well, yeah, it wants, well, this is not exactly related to ionization energy, but it really wants that electron. If you think about why it would want that electron, adding another electron to the third shell, that electron is going to be more attracted staying on that third shell than something on the fifth shell for iodine, right? Because the fifth shell is further away, so any extra electrons it gets, they're a lot easier to remove.
Yeah. So okay.
So first I would say is fix this, and then this is why, and then we just started talking about why is the chlorine more reactive. So think about what happens at the shell model
Wait,
level.
so I'm trying to remember, is my explanation wrong?
I'll let you fix that.
I just had a question, because I did email this, but I don't remember what you said, but like, I was trying to open electrolytes to volume J and it wasn't working. And
Oh.
it's been working for like a week now.
Oh, let me check that.
I mean, I guess it could be like my
That's
computer.
really what I wrote. I circled
It's possible. Let me do a in private so that it doesn't use my account to open it.
And it's not because of iron, so iron is left over, which means that chlorine was reactive the most because it's the one that's left over. So.
Alright, so electroslides. They still work for me. So it's your browser maybe? If you try
Because like, it'll act like it's loading and it'll take like a minute and
Yeah,
it'll say like error, you know, or
so
something.
is this Safari?
No, this is Firefox.
Can you try an in private session? Because if you do that it'll use no cookies.
Yeah.
And maybe it's you got a weird cookie in there that's preventing it.
Yeah, like there's the.
I mean, so if it works, that's the case. You'll have to like clear your cookies
Yeah.
in the main
Okay.
part. Because I don't want you to clear them if you don't have to, because it's annoying.
Yeah.
It lose all your saved stuff.
Yeah, that's true. Let's see. Open. Yeah.
It works?
Yeah.
Okay, so you can individually find the cookie for the OneDrive thing and
Okay.
try to delete it, or it might even, well, if the URL is showing correctly, then it's the OneDrive thing.
Yeah.